Okay, so let us start today's lecture. So in the previous lecture, we had studied the common emitter, common base and common gate amplifiers. Now let us talk about cascode. Okay. So in the today's lecture, let us talk about this cascode. We had discussed some time back this cascode, but not in detail. So let us talk about this cascode in detail. So before starting cascode configuration, let us also talk about this ideal current source. Okay. So let us say the circuit symbol of a current source can be represented by this circuit symbol, and an equivalent circuit of this current source would be the current in parallel with this resistance. Okay. Now when I say ideal current source, so that means that this current source should provide a constant current which does not even change when the bias voltage of its source changes, right? So that is the current through this, or current provided by this current source is constant. Okay. So constant current even when there is a change in voltage of the source. Okay. So for example, let us say that delta V is the change in voltage of the source, and corresponding to this delta V change in the voltage at the source, the current change, so that should be equal to 0. Okay. So that delta V by delta I should be infinite. Okay. Now the output impedance of an ideal current source, okay, so that should be infinite, right? So the output impedance of the current source, so that should be infinite if it is an ideal current source. Now we had discussed some time back that the BJTs or maybe the MOSFETs also, so they can be used as current sources. So MOSFETs or BJTs can be used as current sources. So we had commented that for example a PMOS or a P-type BJT PNP transistor, so that can be used to pick current from a node, let us say VDD, and supply the current to the node X. Okay. So this can be done by either a BJT or a PMOS, right? So that is, it can pick current from VDD and supply it to node X. Okay. Similarly, NMOS. So I mean this P BJT, that is PNP. So this can be used to source the current. So we called it that we are sourcing the current from here to here. Similarly, NPN transistor. So we had commented that it can sink the current. So it can pick the current from node Y, let us say, and it can sink that current to ground. Okay. So NMOS can also be used as a current source, or NPN transistor can also be used as a current source. It can pick current from this node Y and sink it to the ground. So the job was to sink current. Okay. So both are current sources. PNP transistor can be used to source current, and NPN can be used to sink current. Okay. Now if these two current sources using PNP and NPN, if these two sources, if I say that they are ideal current sources, okay, so then that means their output impedance will be infinite. Okay. So if I say that instead of using some other ideal current source, why not use these current sources? Okay. And for making them ideal, I need to ensure that output impedance is infinite. Okay. So how to make the output impedance of a BJT infinite then? Right. So that is these BJTs, how to make output impedance of these BJT infinite so that they can be used as ideal current source. Okay. So for that, we remember that in a common emitter transistor, okay, so in a common emitter configuration, we had commented some time back that if you put emitter degeneration resistance, okay, then this reduces the gain, but it increases the output impedance. Okay. So the role of this RE, that is emitter degeneration, in common emitter configuration is to boost the output impedance. Okay. But we understand that the gain suffers. Okay. So for example, if the one can write the gain of this common emitter configuration with RE, okay, minus GMRC by 1 plus GMRE. Okay. So if there is RE, then 1 plus GMRE has to be there in the denominator. Otherwise, it is simply minus GMRC, okay, when lambda is 0. Okay. So, but if you include RE, then obviously the gain goes down because of this RE. Okay. But the output impedance, so this increases. Okay. And if I want to use this BJT as a current source, then I need to ensure that output impedance is infinite. Okay. So to improve the output impedance, one can use emitter degeneration resistance in a common emitter configuration. Okay. And we had calculated the output impedance of this configuration earlier as this much. Okay. In our previous lectures, we had calculated the output impedance as this much. Okay. Now, instead of using emitter resistor, okay, so for example, in the previous slide we had seen there was a common emitter or transistor configuration with emitter resistor. Okay. Now, instead of using this emitter resistor, okay, this Q2, that is this transistor, can be used. Okay, that is this RE can be implemented by using this transistor Q2. Okay. So this RE will be replaced by the impedance looking into the collector of this BJT. So that is, let us say, RO2. Okay. So that is RE is now equal to RO2. Okay. And this stage is called cascode. That is common emitter with emitter degeneration. So this emitter degeneration resistor is replaced by Q2. So this is called a cascode. So the job of this Q2 is to provide emitter degeneration. Okay. So this acts as an emitter degeneration for emitter degeneration, and it also acts as a current source. Okay. So this Q2 acts as a current source because we had already discussed in the previous slide that if I want to sync the current from node Y to ground, I can use a NMOS or a NPN BJT. Okay. So this NPN BJT can be used instead of RE. Okay. So instead of RE here, one can use NPN BJT, that is Q2. So Q2 can be used, okay, for providing both emitter degeneration, and it is also used as a current source. So that means cascode is basically a common emitter with emitter degeneration or a common emitter with current source at the emitter. Okay. Now for this circuit, one can find out the output impedance. Okay. So the output impedance of this circuit has already been known to us. Okay. So output impedance of this circuit is known to us. We have already written over here. Now output impedance of this circuit where we have Q2, so RE is replaced by RO2. So one can simply replace in the previous equation of output impedance, one could simply replace RE by RO2. Okay. So that gives me the output impedance of this circuit. Okay. So the output impedance can be written. So RE is replaced by RO2 here and RO2 here. Okay. Or one can further simplify this to that R out is this much. Okay. So R out can be written that R out is this much only. Right? Considering this, uh, one can consider here. In fact, this should be GM1 here. Okay. So one can consider that GM1 is 1 plus GM1 RO2. So here GM1 RO2 parallel to R by 1 is much greater than RO2, right? So once we do that, one can simplify this to this equation. Now in this cascode configuration, one has to also ensure that beta 1 of Q1, okay, that is beta of this transistor Q1 is much larger than 1. So this will ensure that IB is very small, so that the collector current IC1, okay, so that the collector current through IC1, that is collector current IC1, so this will be equal to the emitter current IE1, okay, or the collector current of the Q2. Okay. So if beta 1 is much greater than 1, so one can ensure this relation. Okay. Now if you assume that VBE of Q2 is 0.8 volts, okay, then this node potential, that is the collector of Q2, okay, that is this point VC2, let us say. Okay. So this VC2 can go as low as 0.4 volts. Okay. So if I keep this 0.4 volts, so that means here I have 0.8 volts VB and VC2 is 0.4 volts, so that means this Q2 is in saturation, right? Because emitter base junction, sorry, collector base junction, so collector base junction becomes forward bias, so this is in saturation. Okay. Now the maximum output impedance of this cascode, okay, so this is limited by R pi 1. Okay. So in the previous equation, if I assume that RO2 here in this equation, if I assume RO2 is much greater than R pi 1, okay, so RO2 is much greater than R pi 1, then R out can be written, so R out will be equal to then GM1 RO1, okay, R pi 1. If RO2 is much greater than R pi 1, then R out, that is total output impedance, which is also the maximum output impedance, so that will be equal to GM1 times RO1 times R pi 1. So that means this impedance, output impedance, is limited by this R pi 1. Okay. Yeah, so same R out maximum output impedance is written over here, GM1 RO1 R pi 1. Okay, and GM1 R pi, GM R pi, right? GM R pi is beta. So GM and R pi. So product of GM and R pi is beta 1. So R out max is beta 1 RO1. Okay, and this R out max, that is output impedance of this cascode. Okay, output impedance of cascode. So this is much higher than common emitter stage. Okay. So common emitter stage, let us say, so common emitter stage output impedance, that is looking into this port, so we had calculated, so that is somewhere equal to RO2, right? So the output impedance of common emitter stage is RO2, but output impedance of the cascode stage is beta 1 RO1. Okay. So you're multiplying this beta with RO here. Okay. So that means that the output impedance of cascode is much higher than the output impedance of common emitter stage. Okay. Output impedance of common emitter stage is only RO, and here it is beta RO. Now, similar to NPN cascode, one can also implement a PNP cascode stage. That is, instead of using only N-type BJT, NPN transistor, one can use PNP transistor to implement the cascode stage, or which is called PNP cascode stage because it has only PNP transistors. Okay. So in a PNP cascode stage, so again we'll go by the general definition of cascode. That is, cascode is a common emitter with emitter degeneration. Okay. Emitter degeneration or current source. Okay. So we'll go by this definition. Cascode is a common emitter with emitter degeneration or current source. Okay. So here this Q1. Okay. So this is acting as a common emitter configuration, and Q2 is acting as emitter degeneration transistor. Okay. So if I try to make a PNP based common emitter configuration, okay. So PNP based common emitter configuration, right? So this is PNP based common emitter configuration. Sorry, this is not PNP based common emitter. We'll have to connect these two here and this one here, right? And output is taken as at the collector. So output is taken at the collector. This is V in, V out. Okay. So that is, this acts as an emitter degeneration resistor to this PNP transistor. Okay. So this is a common emitter with RE or emitter degeneration, okay, using PNP transistor. Okay. So here RE can be replaced by this Q2. Okay. So this becomes a PNP cascode stage. Okay. Now we'll again go by this definition, that is, this is providing emitter degeneration and at the same time it is acting as a current source. Okay. So PNP transistor can source current from this node to this point here. Okay. So we had already drawn here the current source using PNP, which takes current from VDD and supplies it to node X. Okay. So it can be used to source the current or it can be used as a current source, right? So here also in a PNP based cascode, this is working as a current source. Okay. Now for this circuit also one can find out the output impedance, and the output impedance of this circuit will be exactly similar to the output impedance calculated for NPN cascode. So I'll write here NPN cascode. Okay. And the NPN cascode's output impedance is this one. So exactly similar output impedance for PNP cascode, that is Rout is GM1 RO1 and RO2 parallel to R by 1, right? So looking into the collector of Q2, the impedance is RO2. So RO2 is in parallel with R by 1 now here. Okay. Now let us also consider some configurations which look like cascode, but they are actually not cascodes, right? Or we call false cascodes. They appear like cascode, but they are actually not a cascode, right? So for example here, okay, so this circuit looks like a cascode, okay, but this is actually not a cascode, so that can be verified from here. So this transistor Q2, okay, so this is acting as an emitter degeneration or current source, so which is not true. Okay. So I have a common emitter NPN to which at the emitter this PNP is connected, okay, for working as emitter degeneration or as a current source, which is not true. Okay. So why this is not true? So one can notice that uh, this PNP cannot be used for sinking the current. Okay. So we had some time back commented that PNP can be used to source a current. Okay. It cannot be used to sink the current. Okay. So we had commented. Similarly, NPN can be used to sink, but it cannot be used to source the current. Okay. If you try to reverse the jobs, okay, then we saw that the change in the node potentials at X or Y, so they were changing the base to emitter voltage. Okay. That is, base voltage was changed. Okay. So we don't want that to happen. So that is why this circuit cannot work as a cascode. So it's a false cascode, okay, where Q2 does not work as a current source. Similarly, this circuit, this one. Okay. So this also looks like a cascode, but it is not a cascode. Okay. Okay, so here output is taken here at this point. So that means uh, Q2. So that should act as RE, okay, or a current source. Okay. But since this Q2 cannot be used to source the current, it can only be used to sink the current. Okay. So this is not acting as a current source. Okay. So in fact, in the small signal model, if you draw, then you will see that this is basically a diode connected transistor Q2 here also. Okay. So it's not working as a current source. So this is a false cascode. Okay. Now for this circuit also one can find out output impedance, and you will see that the output impedance of these two configurations, so these are different from the output impedance of the cascode that we have calculated, a PNP or NPN cascode. So the output impedance here is different. Okay. Now before finding out the gain of this cascode stage, let us discuss about the short circuit transconductance. So for example, I have a circuit with some input. Okay. So here input and here we have output. Okay. So for finding out the short circuit transconductance, we need to short the output to the ground. Okay. So output node is shorted to the ground, and then we find this I out by V in ratio. Okay. So I out by V in ratio when output is shorted to ground. Okay. So I out by V in when V out is 0 or V out is shorted to ground. So this gives me short circuit transconductance GM. Okay. So capital GM is short circuit transconductance, which is obtained by shorting the output node to ground and finding out I out by V in ratio. Now using short circuit transconductance, one can calculate the voltage gain of, for example, this circuit. Okay. Now this circuit can be transformed into this circuit, that is this is actually the Norton equivalent circuit of this. So where you have I out and R out in parallel. Okay. Now one can short the output to ground and find out I out versus V in ratio, I out by V in. Okay, so that would be my GM. Okay. And from this circuit one can write V out as minus I out times R out. Okay. V out as minus I out times R out. Okay. And I out can be written as GM times V in. Okay. So from here this I out can be written as GM times V in. Okay. So I out here is written as GM times V in. Okay. So this gives me V out is minus GM V in R out. So from here I can find out V out and V in. So V out is present over here, V in here. So V out by V in would be equal to minus GM times R out. So this is the gain of this circuit. Okay. So the gain of this circuit in terms of short circuit transconductance would be equal to minus GM times R out. Okay. I'll write AV, that is gain is minus GM times R out. And where GM is I out by V in when output node is short circuited. Okay. So this relation I can now use for finding out the gain of the cascode. Okay. So for example, let us use the short circuit transconductance to calculate the gain of this circuit. Okay. So this is a common emitter configuration with current source placed on the collector of Q1. Okay. So for finding out the GM, we short the output to ground, okay, and find out I out by V in. Now the small signal circuit can be drawn for this circuit, right? So a small signal circuit will consist of R pi here and V pi dropped across R pi and GM V pi and R naught. Okay. So I out would be equal to GM V pi, okay, because V out is 0. So I out is GM V pi. So I can write I out as GM V pi. Okay, and V pi is V in. So I can write I out is equal to GM times V in. Okay. Or I can write I out by V in. I out by V in as GM. Okay. So this is also the short circuit transconductance. I out by V in. So which is equal to GM. So I can write this capital GM, that is short circuit transconductance, is equal to GM1. Okay. Now the output impedance of this circuit can be found by this circuit. Okay. So for finding out the output impedance, you connect a small voltage and you measure the current at the output. Okay, and then find Vx by Ix ratio. So Vx by Ix gives you R out, so which can be found from this small signal circuit. We had done this earlier. Okay, so draw the small signal and then find out the Vx by Ix ratio, which is equal to RO1. Okay, so R out of this circuit is RO1 and GM is also calculated, R out is also calculated. Okay. Now for finding out the gain of this circuit, AV, okay, so we had said that the gain is minus GM times R out using short circuit transconductance. Okay. So here also the gain of this circuit would be equal to minus GM times R out. So GM we have calculated here, R out also calculated. So simply multiply GM and R out. So the total gain of this circuit is minus GM1 times RO1. Okay. So GM is GM1 and R out is RO1 from here. So total gain of this circuit is minus GM1 RO1. Now the same procedure can be applied to find out the gain of a cascode stage. Okay. So for example, this cascode stage. So the gain is again minus GM times R out. Okay. And R out for this cascode we have already calculated. So I'll take you back. R out of cascode we had calculated here. So that R out is GM1 RO1, okay, RO2 parallel to R pi 1. Okay. So same R out can be utilized to find out the gain of this circuit, right? So gain of this cascode is minus GM times R out. So gain of this circuit is minus GM times R out. So R out is known to us. Okay. Now GM of this circuit. Okay. For finding GM of this circuit, I'll have to find out I out by V in. Okay. So I out by V in, we have to find out. Okay. And that I out by V in, so that is already found. That is, this is equal to GM1. Okay. So R I out by V in is already found, which is equal to GM1. So the gain of a cascode can be written simply by using R out, which we have already calculated, and GM we have also already calculated. So which is equal to this much now. Now similarly, so this is for cascode. So now let us also compare the gain of cascode with the gain of common emitter. So this is common emitter stage. Okay. So for a common emitter stage, the gain we have already found, which is minus GM1 RO1 in the previous slide here. Yeah, for this circuit it was minus GM1 RO1. Okay. So gain of common emitter is minus GM1 RO1 and gain of this is this much. Okay. Now this gain is greater than the gain of common emitter. Okay. So one reason for why this gain is greater than the gain of common emitter, because the impedance of cascode is greater than, or impedance of cascode is larger, okay, than common emitter output impedance, right? So R out, that is output impedance of cascode, is larger than the output impedance of this common emitter. So that is why the gain is also larger. Okay. Yeah, so this is same, that is one can find out the gain by calculating I out by V in. Okay. So I out by V in by shorting the output to ground. So one can find out I out by V in. In fact, this one can write I out is equal to GM1 V in. So I out by V in is equal to GM1 here, or GM is GM1. Okay. And R out we had already calculated. So one can write AV as minus GM times R out, that is minus GM1 times R out. Okay. So one can find out the voltage gain of cascode amplifier using this short circuit transconductance GM. Okay. Now in a cascode, okay, so this was my cascode here, so in which I was using Q1 for as a current source. Okay. Now this current source, we had assumed that it can be ideal, okay, but no current source is ideal. So output impedance is finite, not infinite. Okay. So this circuit now can be changed by considering another transistor Q3 as a current source. Okay. So Q3 is now acting as a current source here, that is, it draws current from VCC and supplies to this node. Okay. So one can find out the output impedance of this, that is impedance at this point. Let us say total R out T. Okay. For this cascode pair, we have already found output impedance R out. And for this Q3, looking into the collector, we know that impedance is RO. Since it is Q3, so I'll say RO3. Okay. So the total output impedance of this circuit would be the output impedance of this cascode, which we have already calculated in parallel with RO3. Okay. Or further, you can simplify this circuit by considering RO3 in place of Q3, okay, and knowing R out of cascode. Okay, so R out cascode is already known to me. Okay. Now total R out can be found by saying R out cascode parallel to RO3. So this will give me total R out, and R out cascode is known to me, so which is this much. Okay. So R out cascode we have calculated. I'll take you back to this slide where we had mentioned R out cascode. X for cascode output impedance, which is this much, GM1 RO1 multiplied by RO2 parallel to R by 1. Okay. So same output impedance is valid in this circuit here for this cascode. Okay, that is Q2 Q1, so GM2 RO2 R1 parallel to R by 2 and in parallel with RO3. So one can write the output impedance of this circuit. Okay. Now one can improve this circuit by considering a PNP cascode current source. Okay. So this portion, that is, which is composed of Q3 and Q4 transistors. Okay. So this is a PNP cascode. Okay. Or a PNP cascode current source. Okay. So this PNP cascode current source is drawing current from VCC and supplying to this node. Okay. Now output impedance of this can be calculated, the overall circuit, because we know the output impedance of PNP cascode and the output impedance of NPN cascode. So we know that. Okay. So the total impedance R out would be equal to the parallel combination of the output impedance of PNP cascode and the output impedance of NPN cascode. So output impedance of PNP cascode is this much, we had already calculated, and NPN cascode also we had calculated already. So we'll use the same values here. So total output impedance is this much now. Now one can find out the gain of this circuit also. Okay. So the gain will be given by again the same relation, that is minus GM1 R out. R out is already with us. Okay. And GM, so this is equal to GM1. Okay. By shorting the output to ground, one can find out I out by V in. Okay. So which comes out to be equal to GM1. So total gain of this circuit would be equal to minus GM1 times R out. Now so far we have talked about the cascode using BJT only. Okay. Now the same cascode can also be implemented if I use a field effect transistor. So for example, NMOS cascode stage has been shown over here. Okay. So this is similar circuit. Circuit is same, only the devices, that is these transistors, are replaced. So instead of BJT, now I'm using a MOSFET. So this is NMOS cascode stage. Okay. So in this NMOS cascode stage, again you will find this is acting as common emitter, and this M2 is acting as source degeneration. Okay. So the total output impedance can be found. In fact, it remains same, similar to what we had calculated for a BJT based NMOS cascode stage. Right? So it remains same, the output impedance. Yeah, it remains same, correct. Now, similar to NMOS cascode, one can think of using PMOS in the cascode. Okay, so we are using a PMOS transistor here in this cascode, which is called PMOS cascode stage. So again, this is the source of M1. So to this source, M2 is acting as source degeneration or current source, that is drawing current from VDD and supplying to this node X. Okay, so this is a current source here or source degeneration. Okay. Now the output impedance of this circuit also remains same, similar to what we had calculated for BJT. Okay. Same is true for a PMOS cascode as well. Okay. So the total output impedance is this much of a PMOS cascode stage. Okay, so I think this is same. So yeah, so let us discuss this one also. So we had seen that a MOS cascode can be thought of as a common source stage to which source degeneration is connected. So for source degeneration, M2 is used, or one can call it as a current source, which is sinking the current to ground. So it is picking current from X and sinking it to ground. Okay. So RS, or current sink. Okay. M2 is acting as source degeneration or current source for sinking the current. Okay. Okay. So this is similar to a BJT cascode. So in the BJT cascode also, we had seen that the two transistors were stacked on top of each other. Okay. So here also MOSFETs are stacked on top of each other. Okay. Output impedance was also same, calculations were same. Okay. The only difference is that here the output impedance is not limited by beta. Okay. So unlike the bipolar cascode, the output impedance in the MOS cascode is not limited by beta. Okay. Now we also understand that in a MOSFET, parasitic resistance between drain to source can be present. Okay. So that is, in between drain and source of M1, let us say there is a parasitic resistance RP. Okay. Now the effect of this parasitic resistance on R out should also be estimated then. Okay. So effect of this parasitic resistance on R out is that, so apart from RO1 of M1, now RP is also existing in parallel with RO1. Okay. So for M1 transistor, now RP is also in parallel with RO1. Okay. So in the output impedance equation that we had calculated for this stage, okay, so wherever I see RO1, I'll keep RP, that is between drain and source we have a parasitic resistor over here, and RO1 for M1, so RO1 parallel to RP, so that we will add. Okay. So that is total output impedance will also see a contribution from RP. Okay. So that is the total output impedance of this stage can be written as, okay, so here we have R01, so R01 in parallel to RP. So wherever I see R01, I have to keep RP in parallel with R01. So the effect of parasitic resistance is that the total resistance of the cascode, so that or total output impedance, so that is actually lowered. So let me go back here and check. Okay. So the total output impedance now has a contribution from the parasitic resistance. Okay. So total output impedance has a contribution from this parasitic resistance, and the effect of this parasitic resistance is that the output impedance is lowered or it reduces because of this RP. Okay, so this we can skip because transconductance we have already seen, short circuit transconductance. Now for this circuit, which can be used as a MOS cascode amplifier, okay, so one can find out the gain of this circuit, so which will be simply equal to minus GM times R out. So R out for this circuit we have already calculated, okay, considering no RP here, okay, and the total gain is then this much. Now one can also think of using a PMOS cascode current source as load. Okay, so earlier we had seen NMOS cascode current source as load. So one can also think of using a PMOS cascode current source as a load. Okay. So again, the job of this is to source the current from VDD and supply it to V out node. Okay. So total output impedance, we had commented that one can calculate the total output impedance if I know the output impedance of this PMOS cascode and the output impedance of the NMOS cascode, that is this one. So both have been calculated earlier. These output impedances have been calculated. So R out will be simply parallel combination of these two impedances. Okay. So R on we had calculated RO of NMOS cascode. For PMOS cascode also output impedance we had calculated. So total output impedance is this much. Okay, so we had seen, in fact this is the same slide, it's a repetition, which says that the output impedance of this common emitter configuration can be increased or boosted if you put a emitter degeneration resistance or a current source at the emitter. Okay. Yeah, so this also we had seen that another view of cascode could be that you have a stack of transistors. Okay, that is BJT stacked over another BJT. Okay. And one can find out the output impedance. So we had seen this. Now let us talk about another important concept. In fact, we'll cover that in the next class, the details. But yes, let us discuss here that the concept of this current mirror. Okay. So we'll discuss in detail the current mirrors later on in the next class. Okay. So a current mirror, right? So for example, I have this circuit, okay, and to bias this circuit, that is to set the collector current I1 for this circuit, I am using these two resistances. So these two resistances are used to bias this circuit, that is set the collector current. Okay. Now from this circuit one can find out this current I1. Okay. So this collector current can be found. We had learned how to find out this collector current by simply using the diode equation. Okay. PN junction diode equation. So this collector current or I1 through Q1 is given as IS times e to the power VBE by VT. Okay, IS is saturation current. Now in this current equation, we see that this depends upon both VBE and VT. Okay. That is the bias point, that is I1. So this depends upon both the supply voltage and also it depends upon the temperature. Okay. And if any of these two things change, then this bias point also changes. Okay. Now if I can design a current source which does not changes with the supply voltage variations or temperature variations, okay, then that current source can be used here at this point to bias this transistor. Okay, so then this circuit will be more stable, because now this circuit is not much stable because the bias current, this depends upon both the supply voltage and the temperature. Okay, because VT also depends upon temperature. VT is KT by Q. Then saturation current, so this is largely dependent on temperature. More is the temperature, more is the saturation current. Okay. So that means this bias current depends upon these two factors if I use this circuit to bias this transistor. Okay. So my need is that I want some bias circuit which produces a constant current, and that constant current does not depend upon variations in supply voltage and variations in temperature. Okay. So if I can design that source of current, so then directly I can apply that current source here to bias this transistor. Okay. Now for this purpose, okay, so forget this golden current source. Okay. So for this purpose, if I have some current source which is ideal, right? So let us say I have designed some current source which does not vary with the bias voltage and temperature, and let us say that is my reference current source. Okay. Now the next job is to copy this current source in various locations at the integrated circuit, right? So in an integrated circuit, an IC, you may require to use this current to bias many transistors, and there are millions of transistors, millions, not millions, in fact trillions of transistors on integrated circuits, trillions of MOSFET. So to bias this trillions of MOSFET, one would need to copy this current at trillions of locations. Okay. So how to copy this current? Okay. So to copy this current to trillions of locations in a MOSFET, there could be another circuit which may be called as current mirror, that is, which will mirror this ideal current source to many locations, okay, trillions of locations. Okay, I copy, similarly I copy. Okay. So this is the job of my current source. So in fact we'll talk about this, current mirror. So we'll talk about this current mirror in detail in the next lecture. So I'll stop here. If you have any queries, then you can ask.